black holes and black strings.
Great, thank you very much for the invitation. So today I'll be talking about a new class of gravitational solutions that computes the index for black holes and black strings in a variety of examples. And this is work done together with Joaquin Turiachi, Samir Murthy, Roberta Emparan, and my graduate student, Jan Borov. So before I start going into detail about these solutions, let me just summarize the big picture. So ultimately, we'd like to describe any gravitational system, such as a black hole, in terms of properties of a dual quantum mechanical system. And we'd like to do this not only in ADS, but also in any space-time, for instance, space-times that are asymptotically flat, that are closer to our own universe. And to be more concrete, how we would like to realize this duality more broadly is that by imposing a certain class of boundary conditions, for instance, we can fix the inverse temperature and turn on some sources at the asymptotic boundary of a space-time. We'd like to match the quantity computed in gravity by the same an analogous quantity in a conventional quantum system, in this case, a partition function computed at a given inverse temperature in the presence of the same sources for some of the operators in the quantum theory. Now, as all of you know, this dream about holography has been realized in the context of ADS-CFT by considering a large stack of branes that back reacts on the space-time. And in the limit in which we take the temperature at asymptotic infinity to be 0, the resulting back reaction causes the space-time in the near horizon region of the branes to take the form of an ADS space-time times a compact manifold. And because we're taking temperature to 0 at asymptotic infinity, not in flat space, I mean, we can, this part of the space-time is actually infinitely long, and we can zoom in onto it and forget about the rest of the space-time, forget about the flat space part. And this is typically called the decoupling limit, and it's the 0 temperature limit from the perspective of flat space. And in principle, taking this decoupling limit doesn't necessarily imply that the temperature in the ADS region is also 0. It could actually be finite. So in this duality, as all of you know, we typically compute the quantity in gravity like a partition function, where we can turn on an inverse temperature at the ADS boundary and turn off some sources, and that's what we match on the CFT side. But a natural question is whether we can forget about this decoupling limit altogether and go away from it in a controlled fashion. And today, I'll tell you about how to do that for at least some observables, namely for supersymmetric indices. What are supersymmetric indices, and why would they help in going away from the decoupling limit? Well, let's imagine that we want to describe an index in a dual quantum system. The index in a supersymmetric theory is the same as a partition function, but instead of just having a factor of e to the minus beta h, sorry, I thought this needs to have a minus. It also has an assertion of -1 to the f that counts bosonic and fermionic states with different charges. And for instance, we can take the trace either over all states in the theory, or perhaps only look at a certain charge sector. If we only look at a certain charge sector, then this expression for the trace in general becomes very simple. It's just given by the Boltzmann factor that's just weighted by the BPS energy of the states that contribute. Those are the protected states. This BPS energy just depends on the charges. And this is multiplied by the difference between the bosonic degeneracy of protected states minus the fermionic degeneracy of fermionic states. As you can see, the index has a trivial beta dependence. For instance, if I take the log of the index, it should be linear in beta, right? The index in principle can be computed at any temperature, not even though only protected states contribute to the index, and all unprotected excited states that would give a non-trivial temperature dependence don't contribute. In principle, it can be computed at any temperature. So if you can really view the gravitational objects as dual to quantum systems, even in flat space, the fact that we can choose the temperature to be whatever we want could in principle allow us to interpolate between the decoupling limit, the zero temperature limit, and the finite temperature limit to find the gravitational solutions that capture the index of the same quantum system. And today I'll tell you how this happens for black holes in 4 and 5 dimensions, whose horizon topology is S2 or S3. And I'll also talk about the example of black strings, which are more, lead to a familiar example of the ADS-CFT duality, whose horizon is S1 cross S2. So indices themselves have already long been associated with the decoupling limit, precisely because the index only receives contribution from the ground state in a given charge sector, right? So you might think that when you look at the index is the same as taking zero temperature, but this has long been a misconception. And you could view this misconception when thinking about the famous equality between the index computed at string coupling for black hole states and the area computed, the area of extremal black holes in a fixed charge sector. So as most of you know, Strominger and Vafa computed matched an index in string theory that was computed at weak coupling and matched that index to the logarithm of that index to the area of an extremal black hole in supergravity with the same charges. But if we look more carefully at this equality, there are 3 problems arise. The first problem is that the right-hand side, if we look at black holes that are extremal, the quantity computed on the right-hand side is a zero temperature quantity, and at most it's computing a degeneracy, while the left-hand side is defined for any temperature, as we just saw earlier. The second problem is that the left-hand side counts bosonic and fermionic states with an opposite sign, as we saw in the fact that dB minus dF appeared explicitly. And the third problem is that there could be many other extremal solutions that should contribute to the left-hand side. And while it's unclear what we should do with these other extremal solutions on the right-hand side. So for instance, if we talk about multi-center configurations, multi-center black hole configurations, should we sum the areas and match that to the index? If so, why should we sum the areas? Are the entropies of each individual black hole independent? There's many questions that arise. Yeah.
Ask a question about problem 2.
Yeah.
I thought that at least in sufficiently supersymmetric examples, there are no minor sign. So in other words, the index actually counts the degeneracy.
No, I don't believe so. In flat space, for instance, that's not the case. You could, in principle, have both bosonic and fermionic protected states in any given charge sector. So
even with a lot of supersymmetry, let's say half BPS states and n equals to 4, n equals to 8.
Oh, sorry, with even more supersymmetry.
Yeah, I don't know how much supersymmetry you're assuming.
Yeah, so here I'll be looking at black holes in flat space and n equal to 2 supergravity. In general, if a black hole solution exists, then there's always the risk that there's always there could always be both bosonic and fermionic states that are BPS in a given charge sector. And that same happens, I think, in N=4 super Yang-Mills. If you look at 1/16 BPS states, which are the ones for which black hole solutions are known, there are both bosonic and fermionic states in principle in any given sector.
But in Stroman-Shirvafa, for example, I think it's not the case in the original.
Even there, I think it's the case, but we can discuss afterwards. Or at least I don't see I thought it was the case. Great. So what's the problem? Why can't we just compute the index directly in gravity at finite temperature and count bosonic and fermionic degrees of freedom with an opposite sign? Well, in general, to compute an index, the other thing that you could do instead of inserting -1 to the f is if you write that trace at the path integral level, you could impose that all fermionic fields are periodic around the thermal circle, right? So on the gravity side, this would tell you that you have to compute a bulk quantity in which at the asymptotic boundary, fermions are also periodic around the thermal circle. Right, and we can set beta arbitrarily. However, if we take a conventional Euclidean black hole solution, famously, the thermal circle is contractible in the bulk. That's in fact how one determines what the temperature of the black hole is from a Euclidean point of view. One starts by weak rotating a Lorentzian black hole solution. And imposing that the resulting Euclidean geometry that one obtains is smooth. And when you impose smoothness, you're essentially imposing that there's no conical singularity at the Euclidean horizon, which is the tip of this cigar. And in this geometry, the thermal circle becomes contractible. Now, if fermions are periodic around this circle, then this geometry does not have a valid spin structure. So it doesn't exist. It shouldn't contribute. So this confusion actually permeated in ADS-CFT. And the long-held belief was that indices on the boundary side received no contributions from black hole solutions because of this. And this was more recently explicitly proven wrong, because people computed the index, the 1/16 VPS index in N=4 super Yang-Mills, and explicitly showed that there is an n² growth of states, which is characteristic of a black hole. So more recently, people also saw this on the boundary side, but I'll review today why from the bulk perspective, this belief was incorrect. And the solution to this problem is that looking at this Euclidean saddle, that's the analytic continuation of a black hole at finite temperature without any rotation, is actually the wrong, you're looking at the wrong saddle. And with these boundary conditions, there are other saddles that are black holes that actually contribute. And to see this, it's actually convenient to rewrite the index on the boundary side, to rewrite this -1 to the f that appears in the index as e to the 2 pi a times an angular momentum. Now, whenever we encounter such a term in a partition function, we'd say that instead of computing the partition function in the canonical ensemble, we're actually looking at a partition function in the grand canonical ensemble with a chemical potential for the angular momentum J. Now, a chemical potential for the angular momentum J is also known as an angular velocity. So the insertion of this -1 to the f just instructs us to look at solutions that have an angular velocity, a Euclidean angular velocity, such that that angular velocity times theta is 2 pi times 1 plus 2 times an integer. That's because for any value of n, this insertion of omega will lead to an insertion of e to the 2 pi j. So in principle, one needs to look at rotating saddles and sum over all such rotating saddles. So let's look at this in the simplest possible setting. Let's take a solution that we all learn about in GR. So a solution that we all learn about in GR that's rotating is just a rotating black hole in Einstein-Maxwell theory, also known as a Kerr-Newman black hole. So what happens to these solutions if we turn on these specific angular velocities? Does anything crazy happen that suggests that we're computing an index? And the answer is yes. So let's take that solution, and once again, we rotate it by sending t to minus I tau, in which case the Euclidean angular velocity just becomes I times the Lorentzian angular velocity. Now, when I weak rotate rotating Lorentzian black hole, it turns out that importantly, the thermal circle is not actually the contractible circle in this geometry anymore. That's only true in the absence of rotations. And that's what actually led to the confusion for a really long time in the context of ADS-CFT. If rotations are turned on, then the circle that is contractible is a linear combination between the tau and phi circle. And the identification that one makes is that tau needs to go to tau plus beta and phi needs to go to phi plus beta omega. So as we roll around the thermal circle, we also rotate around the sphere. Now, let's insert beta omega to be 2 pi. This consequently implies that a fermionic at the asymptotic boundary that goes around both the tau circle and the phi circle should be anti-periodic, right? Because that's the contractible cycle in the geometry. But the fact that this fermion is anti-periodic around this cycle implies that if I only do a rotation around the thermal circle, the fermion remains periodic, which is exactly the boundary condition that computes an index. So now let's actually check that the associated free energy for these black holes has the structure of an index. So for that, you have to compute the on-shell action of these solutions, the Euclidean signature. And this has been done. It takes a very complicated form in general. But here, I'm just showing you the first term in the large beta expansion, just to show you that a cancellation occurs. You see that if you plug in beta omega to be equal to 2 pi, this term completely cancels. And in fact, you could explicitly check that all subleading terms in beta also cancel. So when you plug in beta omega to be plus or minus 2 pi, you get to this extremely simple result that's exactly linear in the inverse temperature, which is precisely what we expected for the logarithm of an index in any putative dual supersymmetric quantum system. Right? Moreover, this result doesn't only have the structure of the index, but the geometry has additional symmetries for this special value of beta omega. Namely, you could explicitly check that you could solve the killing spinner equations in this background, and you could find that this geometry has a killing spinner, which implies that it's supersymmetric. And of course, this should naturally be the case, because the boundary quantity that we're computing is also protected by supersymmetry, so we'd expect that the bulk solutions that contribute are also supersymmetric. Now, there's a small subtlety, which is I told you that in principle, there's many values of n. There's many saddles that are all rotating slightly differently. All these saddles should be summed up, and all those contribute to this boundary quantity. So what happens to the other values of n? Well, you could even see in this large beta expansion that this term doesn't cancel anymore. These saddles are subleading. This term is negative for any other value of n, besides 0 and minus 1. But in principle, if it contributes to the index, it leads to a puzzle. Because the logarithm of the resulting quantity is no longer just linear in the inverse temperature. So we no longer have a free energy that takes the form of an index. And moreover, you could explicitly check again that none of these geometries have any killing spinners. But it turns out that this puzzle is resolved once you think about quantum fluctuations about this geometry. So if we're in a theory of supergravity, in addition to the metric and the gauge field that we turned on to obtain these solutions, we have a gravitino. And in principle, we also have to integrate over all over all fluctuations of the gravitino that correspond to large superdiffeomorphisms. And it turns out that you could show that in all these solutions, the superdiffeomorphisms that's generated by the superpartner of the large diffeomorphism partial tau is an actual zero mode of the supergravity action. So in principle, if I actually have to integrate over this mode, if I have a genuine fermionic mode, the contribution of those saddles, even though they have non-zero action, their contribution would be zero. Because the integral over a Grassmann variable, as all of you know, is just zero without any insertion. Now, if you have a killing spinner, it turns out that this geometry has a superisometry that's characterized by the killing spinner. And when you do the path integral, in general, you have to quotient your integration space by the space of isometries, or in supergravity by the space of superisometries. And one of the superisometries is precisely this superpartner of this large diffeomorphism. So it's only the geometries that have killing spinners that end up contributing. A side note, this is actually what differentiates regular Einstein-Maxwell theory that we learn about in our GR books from supergravity theories. In principle, if we take n equal to pure supergravity in flat space and only look at the bosonic sector, the theory that we write down is Einstein-Maxwell theory, right? So the saddles, because the bosonic action is the same, the saddles for both theories are identical, right? So these index saddles that I talked about contribute even in non-supersymmetric theories. However, in non-supersymmetric theories, the subleading saddles do contribute to this partition function, while in supersymmetric theories, in supergravity theories where there's a gravitino, they don't, because of the presence of this zero mode. So this points to something slightly special, which is that even if I compute the equivalent of an index, so just trace -1 to the FE to the minus beta h, for black holes in our own universe, which is well approximated by Einstein-Maxwell theory for the purpose of studying these black holes, their free energy at leading order actually does look like an index. I don't know exactly what that means, but I think it's an interesting fact that there is an almost exact cancellation between the number of bosonic black hole microstates and fermionic black hole microstates that are excited even within our own universe. Okay.
In a large beta.
No, at any beta. So if you look at this relation is true for any beta. And for any beta, this is not something that's on the slides, but for any beta, you could also show that these other saddles are subleading.
In
G Newton, and 1 over G Newton. Yeah, which is very, very subleading.
Subleading in beta.
No. It's subleading in 1 over G Newton. Okay. So an alternative derivation of the free energy, instead of computing the Euclidean action, you could just wave your hands and say that the Euclidean action or the free energy should just be a sum of the entropy, which is given by the area of the black hole, beta omega j, which is because we turn on an angular velocity in these solutions, minus beta m. And it turns out that even though the geometry has very non-trivial beta dependence, there is a cancellation between the temperature dependence in the area term and in beta omega j that makes it precisely that the sum of these two terms is pi q squared. And m, because there is a killing spinner present, happens to be exactly equal to q. So even though these geometries depend on the temperature, the result has trivial temperature dependence. And I'd like to view this as a baby version of something known as the attractor mechanism. So the attractor mechanism was developed in the 90s, and it was basically the mechanism that it explained why why the entropy of extremal black holes were independent of boundary conditions at infinity. So, when we look at black holes in string theory, there's not only a metric and a gauge field, as in these examples, there's additional scalar fields. And it turns out that the entropy of extremal black holes is independent of the value of the scalars at infinity. Here we're seeing a similar version of independence from the boundary conditions that we place at infinity. The boundary condition that we placed at infinity was that we fixed beta by fixing the size of the thermal circle. And we're magically seeing that that value of beta does not vanish in the entropy, but vanishes in the free energy. And we'll show that this version of this new version of the attractor mechanism holds even when considering other scalar fields in the theory, scalar moduli. So from this first part of the talk, the first take-home message should be that there are flat space geometries with non-zero temperature that still capture the same index as the one seen in the decoupling limit. So in the, sorry, maybe I forgot to mention this result, IQ squared, as maybe a lot of you know, is exactly the extremal entropy of charged black holes. So we're seeing that the dB log of dB minus dF precisely match the extremal entropy that people computed in the past, which explains why, at least in this baby version, why all these matchings made sense. Good. So we're still computing the same index, but now there's no longer an ADS part of the space-time. The extremal black holes used to have an ADS2 float. Now, when we go at finite temperature, there's no longer an ADS2 float, but the black hole is rotating precisely by an amount that's 2 pi as you rotate around the thermal circle. The second take-home message is that the free energy of the black hole index saddles has trivial beta dependence, even though all the properties in the geometry, such as the area of these black holes, has complicated beta dependence. And this is some magic due to the existence of a killing spinner in these geometries. And the third message is that even though it comes from the fact that the rotations of the black hole correctly fix the periodicity of fermionic fields at asymptotic infinity. Instead of thinking about turning rotations on, you could think, what is the most general geometry that has a valid spin structure, that has these periodic boundary conditions for fermionic fields at asymptotic infinity? The answer are these rotating black holes. Now, it turns out there is a much vaster set of allowed contributions to the index besides these black holes. So for instance, one could take multiple of these rotating black holes and put them together. It turns out one obtains another valid contribution to the index in the form of multi-center solutions. So instead of starting with the previous approach, in which we start with a known Lorentzian solution and analytically continue to the Euclidean signature, we'll take a different approach to find these solutions. Namely, we'll just look at the most general geometry in 4D that has a killing spinner and is asymptotically flat.
And Euclidean.
Yes, in Euclidean Einstein-Maxwell theory. There's not much of a difference if you look in Euclidean or Lorentzian. The killing spinner equation is also just weak rotated.
But in the Euclidean setting, you're always taking the metric to be real, everything's standard.
So I'm taking the metric to be real, at least at asymptotic infinity. So I'm taking the space-time to be asymptotically flat, and I'm just trying to write a metric that has a solution to the killing spinner equations.
But it could be complex.
It could, in principle, be complex. The solution that I showed you before turns out not to be a complex solution. Also, what we mean by real versus complex is also a little bit confusing, because you could do the theomorphism of the metric that can make it look real, make the components of G mu nu look real oftentimes. But for instance, if you diagonalize G mu nu locally, it could have some complex components. Let me put it another way. Even standard weak rotations that we talk about, so like the weak rotation of a Kerr black hole, turns out to be complex if I keep the Lorentzian angular velocity real.
And I thought you didn't do that.
Yeah, so I didn't do that, and that's why I obtained the real metric. Yeah.
But actually, so those solutions have a Lorentzian interpretation? I mean,
These solutions?
were the ones you discussed previously?
The ones that I discussed previously, not a direct one, because the Lorentzian angular velocity is purely imaginary. So, but they're purely, they're Euclidean, they're well-defined Euclidean saddles. So it turns out that this problem of trying to find the most general form of metrics that admit killing spinors was solved by Todd in the 80s in the context of 4D n equal to supergravity. And he found that the metric takes the following, for any metric takes the following form. Let me explain what these U and omega are. So X is a three-dimensional space known as a base space, and U of X are a set of two harmonic functions on this base space. So they're just sum over poles. Now, it turns out that if we want the space-time to be asymptotically flat, that fixes the behavior of these harmonic functions at infinity. And it also fixes the fact that the number of poles in the function u has to be equal to the number of poles in the function u tilde. So we can draw base space. And just we'll put red and gray dots where the poles are located. The red poles are that of the function u tilde, and the gray poles are that of a function u. Now,
These hyperkiller.
how
many killing spinors do these have?
One.
Oh, just one.
Just one. Yeah. Now, it turns out that if you solve for the gauge fields, for what the gauge, so this is in pure n equal to supergravity, in which there is a gauge field. If you solve for what those gauge fields are, you can see that these AI and AI tilde are like electric or magnetic fluxes for the gauge fields. So if you surround any of these points by a sphere, you would measure an electric flux that's either proportional to A or proportional to A tilde. Now, if you look at, there's one more field here, omega. It's like a one form on this base space that captures the rotations in these solutions. And it's given by, it has the following equations of motion. It's just omega in principle is just determined by u tilde and u. So once you know the harmonic functions, you specify everything about the solutions. Now, what we have to make sure about is this is the most general solutions to Einstein-Maxwell's equations that have a killing spinor, but we haven't satisfy the equations of motion locally. But we also have to make sure that there's no singularities in the spacetimes. There's no isolated points at which the equations of motion are actually not satisfied, because we only solve the equations locally. In fact, if you try to do that, you quickly run into a problem. You can show very easily from this equation that the integral of if you pick a cylinder that surrounds any one of these two poles, the integral of omega along that cylinder happens to be exactly along this edge of the cylinder, happens to depend on the function u tilde evaluated at the pole of the function u. So it takes, the important thing that you can see here is that integral of omega takes a non-zero value. And this happens even if I shrink the circle as much as I want. So in principle, omega has a divergence. right, that occurs on any that you can see on any point on the line in between any one of the two poles of u and u tilde. So we need to make sure that this divergence that seemingly appears in the metric is not an actual singularity in the space-time, but rather it's a coordinate singularity. So we need to do some transformation to make sure that we can get rid of this singularity. Now, omega changes under coordinate transformations. And in particular, if you do a shift of time by some arbitrary function lambda of the base space coordinates, omega changes in a way similar to a gauge field. From this, you could easily see that if you try to do a constant shift of omega such that you get rid of this piece on the right-hand side, you need to do the following shift of t that depends on the coordinate phi that parametrizes the direction around that circle that I just integrated over. Good. But is this a valid coordinate transformation or not? Well, in Lorentzian signature, time is not periodic, and phi, on the other hand, is periodic. So if I do a shift by phi of phi by 2 pi, this coordinate transformation does no longer brings a point back to itself, as it should. So in Lorentzian signature, this coordinate transformation is not valid, and these north and south poles are genuine singularities in the space-time. The only way to get rid of these singularities is if you set u and u tilde to have the same poles and residues. In that case, omega itself is just the vanishing function everywhere, and we don't encounter this problem that integral of omega is divergent. And the resulting geometry is just specified in terms of a single harmonic function u that has a bunch of poles. And this geometry has actually been discussed a lot in the past. It's a famous multi-center geometry called the Majumdar-Papapetrou extremal solution, which just consists of a sum over poles. And each one of these geometries has an ADS2 front and corresponds to an individual extremal black hole. So you could put multiple extremal black holes together, and that also intuitively makes sense, because extremal black holes have a mass equal to their charge. So the issue with putting multiple black holes together usually comes from the fact that the gravitational attraction between the black holes is stronger than the repulsion due to any other force. But when in the extremal limit, when the mass is equal to charge, it turns out that I could put as many of these black holes in equilibrium, and they'll stay there forever. Great. But now let's see what happens in Euclidean signature. So in Euclidean signature, time is periodic, is period beta. And this allows us to compensate the shift of phi by 2 pi by a shift of t by beta. But that only happens if we relate this transformation of t, this parameter that appears in the transformation of t, to the inverse temperature that corresponds to the size of the thermal circle. Now, this quantity, u tilde times a, also happens to be related to the angular velocity of horizon that would sit in between the north and south pole. In between the pole of u and the poles of u and the poles of u tilde. This quantity, if you explicitly compute it, turns out to be 1 over twice the angular velocity. So if you equate this to this, you again find that beta omega is equal to 2 pi. So this time we started with a geometry that has a killing spinner and is asymptotically flat, has a periodic thermal circle. And automatically we found that the only smooth geometries that allow a killing spinner are precisely the ones that compute an index. So after imposing smoothness, we realized the following thing, that that in between any pole of U and any pole of U tilde, there is something akin to a Dirac string that actually corresponds to the horizon of each individual black hole. So in contrast to the Majumdar-Papapetrou solutions, where the horizons sit at the poles of the function U and U tilde, in this case, the horizon of these Euclidean black holes are actually between any two of the poles of U and U tilde. And you can see that explicitly by surrounding one of the poles by a sphere and checking, for instance, what the proper length of this small circle that intersects the line in between the pole of U and U tilde. If you check that, you'll find that the proper length of this curve is finite. So actually, there's a non-trivial S2 in between these two poles. Now, if you surround a pair of poles by a bigger circle, you could check, by a bigger sphere, you could check that that problem no longer appears. And the sphere is completely smooth. So, as I said, pairs between poles of U and U tilde can be identified with the horizons of the black hole, and I could put as many poles in U and U tilde as I want. And the direction, this direction between a pole of U and a pole of U tilde identifies the axis of rotation of each individual black hole. So how you should view this is that each of these lines is a sphere that's rotating along this direction in such a way that once you go around the thermal circle, each one of these spheres does exactly a 2 pi rotation. And the easiest example of this is if we choose only one pole in U and one pole in U tilde, right? Then we obtain a configuration that has a single horizon. And it turns out that there is a smart coordinate transformation that maps the resulting solution to the finite beta Kerr-Newman solution that we discussed a few moments ago. So this is a generalization of the previous solution that we found to an arbitrary number of centers. So compared to the Lorentzian solution that had a decoupling, a region that decoupled in the near horizon region of each one of these black holes that had an ADS2 probe near each one of these black holes. Now we have no decoupling, but because we turned on a temperature. And again, we can compute the index of these black holes by computing their free energy. Their free energy takes the following form in terms of the residues of the function U and the function U tilde, which are A and A tilde. And if you plug in the relation between the residue and the charges, you find the following simple formula for the index, which is the sum of indices of n individual black holes. And once again, we find that it takes the precise form of an index. Okay, so yeah, once again, the geometry has a very non-trivial dependence on the temperature. For instance, the area of each one of these horizons is temperature dependent. But when we sum everything up into a Euclidean action, we get something that has trivial beta dependence.
The definition of the horizon is what exactly?
Yeah, so actually this is quite subtle here. There's not a very good definition of a horizon in this case, because it turns out that the horizon, usually the horizon in thermal equilibrium is also a killing horizon. But in this case, there is no killing vector that becomes null along this line.
So what do you mean by null? It's the Euclidean geometry. So
well, you could still ask whether the condition that a killing vector becomes null is still true once you recrotate it.
It's like a fixed point.
Yeah. That the horizon is a fixed point of that killing vector. That's still a valid for instance, if you take a Schwarzschild black hole and rotate it, you'll still find that the killing vector that's partial tau has a fixed point at the horizon, right? That's the tip of the cigar. You could even see it visually. Now, if you take a Kerr-Newman black hole, a linear combination between partial tau and partial phi becomes null at the horizon. The horizon is a fixed point of that killing vector. Here, it turns out that these points are not fixed points of any specific killing vector. The only way to somewhat define it is, well, one way is that you could move these points around, move them very far away, in which case you can clearly see that this solution, the solution close to the pole of U and U tilde looks like the regular Kerr-Newman solution. So in that case, you have an approximate killing vector that for which these points are fixed points. The other way to define it is to just surround each of these north-south pairs by spheres and ask what is the sphere with minimal area that is homotopic to a sphere that surrounds both points. And that you could call a Euclidean horizon. It's the same in the Euclidean cigar, right? You could take a sphere and shrink it, and eventually you'll end up on the Euclidean horizon. So it's a somewhat unconventional definition of a horizon, but okay. The horizon is not actually important for any physical purpose here. The important thing is that you just find a saddle that contributes to the quantity that you want. Great. So how about black holes in string theory? Well, as I told you earlier, these black holes have additional scalar moduli that come from vector multiplets. And these moduli were very important in the attractor solutions that were first discovered in the 90s by Ferrara, Kalisch, and Strominger that explained why the extremal area of the black hole is independent of the boundary conditions at infinity. To construct these solutions in Lorentzian signature were constructed in Minkowski, in asymptotically Minkowski space times a Calabi-Yau manifold. Today I'll tell you about how to construct saddles in a space-time that's asymptotically flat, but has a thermal circle that has a finite length times a Calabi-Yau. So the new ingredient compared to what I told you before is that we'll have multiple charges that will be characterized by a vector of charges, gamma, and we'll have a set of moduli x whose boundary conditions will fix at asymptotic infinity. It turns out that we could take the same approach as before and ask in this more general theories of n equal to supergravity, what solutions preserve a killing spinor? And again, we'll find the same kind of solutions that are described in terms of a vector of harmonic functions h. But this time, the way in which these harmonic functions appear in the metric is slightly more complicated. They appear, these harmonic functions need to be evaluated by a function sigma of h, where sigma is known as an entropy function that can be explicitly determined from the prepotential. So here I just gave you an example. For instance, if you take the Calabi-Yau to be T6 and set all the vector multiplets that appear from the dimensional reduction on T6 to be equal to each other, so essentially you only have a single vector multiplet, you can obtain explicitly what the entropy function is in terms of the harmonic functions v, p, q, and u that appear in the vector of harmonic functions h. And once again, the residues of the harmonic functions specify what the value of the charges of the black holes is, and the poles specify in principle where the black holes are located. So you could again try to take these solutions and impose that the spacetime is smooth. And in Lorentzian signature, you will always find that if you impose the smoothness condition, all the solutions that you'll find will have an infinite throat. And that implies that the only valid solutions that are supersymmetric are zero temperature solutions. And it's because in the old attractor mechanism, it's because of this infinite throw that if you solve the differential equations that tell you how the scalars evolve in between infinity and the horizon, it's because of this infinite throat that the values of the scalars on the horizon turn out to be independent from the values of the scalars at infinity. Now, it's somewhat complicated, but we can again explicitly solve for the values of the scalars everywhere in the geometry. This time, if we instead look at a contribution in Euclidean signature that's smooth, that again turns out to exactly compute an index. So just as before, if you impose smoothness, it just naturally comes out that the only solutions that contribute have to satisfy this relation between beta and omega. So again, you could solve for the scalars everywhere, and you'll find that the scalars are on the horizon this time are actually dependent both on the temperature and also on the boundary values of the scalars. And that's because we no longer have that infinitely long front. But just as in the simplest Kerr-Newman example, even though the area of these black holes and their angular momentum has very non-trivial moduli and temperature dependence, if you sum the two up, or equivalently, if you just explicitly compute their Euclidean action, you will get something that only depends on the residues of the harmonic function. P and U correspond to the residues of the harmonic function, so the charges of the charges in different vector multiplets. And this answer turns out to be completely independent of the moduli values x at asymptotic infinity. Sorry, this should be an x, and the inverse temperature beta. And yeah, this is guaranteed that this from the fact that the space-time is smooth. And this quantity that I wrote here, that's explicitly computed by looking at the Euclidean action, turns out to be exactly the entropy at extremality that people computed in the 90s. But this time, it's just computed from a finite temperature solution. And this is true more generally. If we impose smoothness, we get an on-shell action that takes the following form. It has a part that's linear in beta that in principle depends on the moduli and captures what the BPS value of the mass of these black holes is, and has a piece that is temperature independent that just comes from evaluating that complicated function, the entropy function, on the vector of charges. And again, this is exactly what people obtained in the 90s more broadly for the area of the extremal black holes. And thus, we can interpret this quantity as the logarithm between dB minus dF for these black holes. So even though the index of such black hole has been computed in string theory, right? The analysis that I did applies not only to black holes in n equal 2 supergravity, but also black holes in n equal 8. The solutions are the same. We actually don't have a good boundary CFT description for them. We only have a string theory count, but we don't know exactly what CFT describes, for instance, the excited states of these black holes. So this begs the question whether we can go away from the decoupling limit and look at how we can go away from the decoupling limit in a canonical example in ADS-CFT, in which instead of considering black holes, we can consider black strings or black brains, right? And now put a finite temperature at asymptotic infinity. And for that, we need to go to a higher number of dimensions. Namely, we need to go to at least 5 space-time dimensions. The space-time, sorry, asymptotically, the space-time needs to be at least R5. So the solutions that we'll be looking for have an asymptotics that look like R3 cross S1 cross Calabi-Yau cross another circle, where this circle can be identified with the circle from in M theory. And the analogous Lorentzian solutions, there exist analogous Lorentzian solutions that are described by black strings in the M theory. And these solutions, if you look at them at zero temperature, their near horizon region looks like ADS-free process 2 cross the Calabi-Yau. This part of the space-time, together with the circle, combine into ADS-free process 2. And this gravitational theory turns out to be described by an MSW CFD, which preserves 4,0 supersymmetry. So what we'd like to do is just find the analogous solutions with these asymptotic boundary conditions and understand whether we're still looking at a property of MSW, even though now we're completely getting rid of the ADS-free front. So it turns out that we can generate all these solutions from the 4D solutions, or MD. If you count the Calabi-Yau, you could generate all these solutions through an uplift. And this is something that people did in the past for the Lorentzian solution as well, namely Gaiotto, Strominger, and In developed this uplift formalism. So what happens if we uplift our saddles that computed the index of 4D black holes? Again, it depends on what charges we choose in 4D. Depending on what charges we choose in 4D, we get different solutions on the uplift. So one way of uplifting is if you choose one of the charges, the charge that arises from that's associated to the gauge field that arises from the dimensional reduction on the M-theory circle. If you choose that charge to be 1 and do an uplift, it turns out that you obtain an attractor saddle for 5D black holes that compute an index in asymptotically 5D flat space. And this computation, the fact that this uplift works, essentially tells you that the gravitational path integral, the index contributions to the gravitational path integral of 5D black holes in M-theory can always be matched with the index of 4D black holes in type 2A supergravity, because we started with the type 2A solution and generated an M-theory solution with the same action. More interestingly, if we choose the same charge to be 0, to vanish, the uplift will no longer result in a black hole. It will result in a black string, and that's embedded in 5 dimensions. And these black strings, instead of having an S-free topology, they have a topology that looks like S1 cross S2. So the uplift is actually somewhat more trivial in this case, because the M-theory circle just multiplies the S2. Previously, there was a non-trivial Hopf vibration that happened in which through the uplift, the horizon of the 4D black hole, 4D saddle, became an S-free. So there's various limits that, could I have 5 more minutes? Okay, there's various limits that you can consider when performing this uplift. The traditional limit is to take the temperature in flat space to infinity and take the size of the M-theory circle at infinity to be finite. And this is the type of boundary conditions that lead to the Lorentzian solution that has an ADS-free cross S2 times the Calabi-Yau front. So this is the traditional approach. Now, the other option is to take the 5D, the temperature in flat space, to still be 0, but keep the ratio between the M-theory circle and the radius of the thermal circle at asymptotic infinity to be finite. So this is still a decoupling limit, but something very interesting happens in the front in this limit. Because this ratio is set to be finite, it turns out that the effective temperature that one has in ADS-free is no longer 0. It's now finite. So now what the solution actually generates, the solution computes an index just within ADS-free. So from a flat space solution, we're generating a solution that computes the index in ADS-free of a black hole that looks like a BTZ black hole that's also rotating on this S2 times and the Calabi-Yau. And these contributions to the index in ADS were previously also unknown. Now, finally, you could also do something that's more akin to what we did throughout the rest of the talk, and just set beta 5D to be finite, and the size of the M-theory circle to be finite. In this case, we completely get rid of the ADS throw, and we just have a black string whose horizon is S1 cross S2 that has a finite throw. So there's no sign of any ADS spacetime or any BTZ black hole within the spacetime. But what all these geometries have in common is that they compute the same index. So explicitly, if you compute the Euclidean action of all these three geometries and subtract the trivial linear and beta term, you'll find that the Euclidean action computes the same quantity in all cases, and it's precisely the log of the index of the MSW-CFT, at least in leading order in the central charge. So here, gamma A, gamma B, and gamma C are charges of branes that determine the central charge of the CFT, and gamma 0 determines the charge of the black hole that you're looking at in the gamma 0 determines the charge sector that you're looking at within the MSW-CFT. Okay, so the take-home message here is that we found gravitational solutions that contribute to the index in conventional ADS-CFT examples. And in principle, I don't think what we did is restricted to black holes or black strings. It can, in principle, be applied to black branes and any of the conventional solutions that have led to the traditional ADS-CFT examples. So any of those could likely be taken away from the decoupling limit in this controlled way. The explicit example that we see of these was for the black string, where even though there's no portion of ADS free in the space-time anymore, we're still computing the index in the CFT. We're still matching the index in the CFT. But in general, if I want to compute an index in flat space, as I said, there are more contributions that don't necessarily appear in the decoupling limit. For instance, even in this case, there are contributions in supergravity that come from multi-center configurations of black rings and black holes. So we can come up with configurations of black rings that rotate along individual directions. These black rings correspond to have the same index as the black strings that I just described. Their horizon looks like S1 cross S2. They're each described by their own CFT that could have different central charges. And in addition, there is like black holes whose microscopic description is still unknown. But now we're capturing their index in a unified way. We're just doing a single calculation and seeing all these contributions. And in fact, we can explicitly compute the action of these more complicated multi-center solutions. And what we find is that the total Euclidean action is a sum of the individual indices coming from each black hole. This is at least at leading order in G Newton. Even more interestingly, it turns out that the Euclidean action exhibits a phenomenon of wall crossing that happens, that also is known to happen when looking at the index in string theory. So namely, the index can jump discontinuously along walls of marginal stability. In our case, we find that if we vary the moduli appropriately, we lose some of the Euclidean solutions, and therefore we lose some of the saddles that contribute to the path integral, and the corresponding gravitational index also jumps discontinuously. The interesting thing is that all these solutions have a very rich moduli space that seems to be much richer than the one in Lorentzian signature, and we're still trying to explore it. And finally, it will be interesting to try to understand whether one can perform a supergravity localization computation around starting with the solutions that I just talked about. The general principle for which we obtain these solutions is to impose that the solutions have a Killing spinner and satisfy the equations of motion. It turns out there's still pretty strong constraints on how the metric looks like if you only impose that there's a Killing spinner without satisfying all the equations of motion. And this will give you the localization locus for solutions that have these boundary conditions that compute an index. And the ultimate dream would be to do such a localization computation in either 10 or 11D supergravity. And there, depending on the choice of charges, you could try to compute the corresponding contributions to the index, and these should correspond to the different supersymmetric holographic CFTs that we know about. Okay, thank you very much. This was it. Any questions?
Are these staff, I mean, are these relevant to anything other than the index, or are there any other observables that these contribute to, like some correlators, or something like that? Or?
Yeah, so I suspect, so we haven't computed anything, but I suspect that if you take any observable that's protected by supersymmetry in ADS, there might be a version of the same observable that can be computed away from the decoupling limit. So for instance, one example of this would be Schur indices, in which you not only compute the trace, but you also insert a Wilson line when you compute a trace, a supersymmetric Wilson line. And there again, in principle, you could compute the index at any temperature, and you could ask whether now you could vary the temperature in the asymptotically flat region and try to find the corresponding solutions. Even just in ADS, I don't think the corresponding Euclidean saddles that contribute to the Schur index are fully understood.
Are the one-loop corrections around these new saddles?
I don't know, because no one has computed them, but I don't see why they wouldn't be under control. As in, it depends what you mean by under control. I don't think there's any divergence that occurs in the determinant of any one of the fields, but it's probably a very hard computation to perform.
I guess you expect the answer to agree with what you compute on those.
Yeah. I would expect that the answer agrees with what you do on the CFT side. Maybe related to this localization computation that I just mentioned, the one loop corrections around the localizing locus can be rewritten in terms of using the Atiyah-Bott fixed point theorem. This is how people usually compute one loop determinants in localization. And this is actually what we did in the supergravity computation a couple of years ago. Here we actually know the killing vector. So the relevant, we know the relevant killing spinner that corresponds to the supercharge with respect to which we would like to localize. We know that the square of that killing spinner, the bilinear of that killing spinner, gives a killing vector. That killing vector is partial tau. Partial tau has fixed points in these geometries, which are precisely at all the poles of the harmonic functions. So I expect that the information about one loop determinants can be obtained from the expansion of all the fields just around these poles of H. But this is just a guess. Maybe one very suggestive thing is that it so happens, I told you that the scalars are dependent on the moduli everywhere on the horizon. Magically, they become independent of the moduli at the boundary conditions of the moduli at these poles. So that also suggests that if you compute the one-loop determinant using some sort of fixed point theorem for the killing vector partial tau, that is also very suggestive that the result you will get will be independent of the value of the moduli at infinity, which is something that you'd want because the one of the moduli determines the string coupling, and the fact that the index is independent of the moduli is independent of the string coupling is akin to demanding that the index is independent of the moduli.
Anybody ever match the entropy of like a black ring or something from some M2 ring theory? So what would be like the simplest example you could imagine?
So yeah, so actually the simplest example in which you can obtain a black ring is if you start with a configuration that's singular in 4D, but is smooth in 5D. Mm-hmm. So it's a configuration that has two charges, one that's has charge 1, 0, 0, 0, 0. So yeah, the uplift of that, it's like the simplest example has charge 1, but that's a singular point in 4D. It can be viewed as a black hole that's Planck sized in 4D. But it turns out that when you uplift this solution, even though you have something that's singular in 4D, it leads to a fine 5D smooth solution. And you can consider one black hole that has this charge, and another black hole that has any charges as long as this component of gamma is set to 0. So this will uplift to a black ring together with some other rotating object that appears from the uplift of the singular point in 4D. And we computed the index of this configuration, and it still matches the MSW index. So I think it's very suggestive that the index of black rings in this theory should just be computing the MSW index with the same charges. Because to obtain this MSW solution, to obtain the MSW solution in the uplift, one also starts with a 4D solution for which one of the poles has one of the components of the charges to be set to 0. So this is what generates the black string. This part is what generates a black string. This part is what generates a black hole. If you put them together, you'll get something that now is asymptotically flat, that computes the mixed index between a black hole and black ring. But if you just choose a black hole that has trivial charges, namely this to be 1 and the rest is 0, it's as if the black ring alone is described by the MSW CFT. Maybe I should clarify. So this is something that people also did in Lorentzian signature to generate the black ring solutions. But the interesting thing is that now in Euclidean signature, the solution looks a bit more like the black Saturn, in the sense that when you uplift this trivial charge, previously that trivial charge in the Lorentzian case uplifted to the origin of the black ring in 5D that happened to be perfectly smooth. This time it uplifts to a rotating Kerr black hole. So the solution looks like, okay, I can't draw in a spatial slice of 5D, but it looks like a rotating Kerr that's surrounded by a ring that carries charge. And the Kerr black hole can rotate along any axis, and individual components of the ring can also rotate along any axis. And the moduli space of these solutions is actually described by the relative orientation of these axes.
And you don't need to know any more about the MSW CFC to match this.
No, just
Charges.
just the, yeah, just the charge and the dependence of the index on the charge.